Yes. In this video, we talk about one more enhancement to the simple parity check method. So, by using simple parity check method, we can detect only 1-bit errors. So, it is not possible to detect more than 1-bit error, that is in positions of even positions. So it is possible to detect 1-bit error, 3-bit error, 5-bit errors. Odd bit errors can be detected easily in previous method that we call it a simple parity check. So in order to detect 2-bit errors or 3-bit errors, what we are trying to do is we are trying to add some enhancement to the previously existed method. That enhancement we call it as two-dimensional parity check code. So in general, in block coding, every message is divided into data units and every data unit is added with redundancy bits. That's a principle of block coding. But in this case, what we do is we take more number of blocks, form a table, and on that table we try to calculate the parity, not on only one data unit. So I repeat, so in general in this methodology, data is organized like a table, and once a table is formed you have rows and columns. Now parity is calculated row wise parity and column wise parity, so that we got more number of parity bits. These parity bits are sent along with the tabular data, so that the receiver can find the syndrome. That syndrome is going to give error notification when you are having more than 1-bit error, also more than 1-bit error, because you are not only calculating parity for one data word. So your data is scattered into different rows and columns. Every row is having a parity. So if there is a change in the syndrome, that indicates your data may be corrupted in one unit or more than one unit, or in one column or more than one column, such that two-dimensional parity check code will make use of this additional logic of calculating parities for each and every row. Now how far it is going to work means, it is going to work up to 3-bit errors. It is going to detect up to 3-bit errors. 1-bit error, 2-bit error and 3-bit errors can be detected, but it is failed to detect 4-bit errors, because if 2 bits are occurred in one row, 2-bit errors are occurred in one row and 2 more bits are occurred in one more row, then these two are neutralized. So if one row is having 2-bit errors and if another row is having 2 more bit errors, these two are get neutralized. So because of this only, this methodology is not working to detect more than 3. That is, it is going to detect up to 3 errors only, and 4-bit errors cannot be detected by this method. So let us see how this data is organized. Now, so if you observe this diagram, so in this diagram, the original data is given very clearly. The original data is given like a data units only, but these data units are formed. These data units are formed like a table. So now we have taken 4 data units, and those 4 data units are organized into tabular related data, like first data unit pushed into first row, second data unit second row, third row, fourth row. So 4 rows are prepared, and after preparing these 4 rows, we are calculating parities for each and every row. So if you take first row, the parity is calculated at the end. Parity is calculated at the end, that is even parity. So as it is having already 5 ones inside it, in order to make that code word to have only even number of ones, the parity bit is added to 1. And similarly, second row, third row, fourth row, and that we call it as row parities. And in order to identify the errors in different places or more than 1-bit errors, again we calculate column wise parities also. Now column wise parities are calculated here, and after that every data unit you take, every data unit is attached with its own row parities. 1 2 3 4 4 data units are added with its own row parities, and one more block is given, and that block is nothing but column parities. That column parities, so column parities is 0 1 0 1 0 1. Likewise you have 7 here, and that's what here added 0 1 z z what way this column these column parities are taken from here, and Here it is going to take column parities, like this column also taken, whatever the parities we calculated, row wise parities, and you got 1 1 0 1, and these all also performed with parity logic, and to get this one, and this total bit is added at the end, this total bit byte, the unit is added at the end. This way column parities are sent like a unit, and every data unit is having its own, every data unit is having its own parity bit. This way at sender side the parities are generated. Once these parities are generated, this entire table is sent to receiver. The job of the receiver is simple. Again he will calculate the parities, all the parities, and he try to calculate the syndrome value, and if syndrome value is non-zero, then there is a problem in the received content, and if it is zero, nothing is wrong, so everything is correct and we have received a original content. This way it is going to work. So let us see how it is going to work at the receiver side. Yeah, see this. For example, we have 2 bit here. If you take one error affects 2 parities, see this. This is the data which is organized in tabular fashion, and when one bit is changed, it is having impact on row parity as well as column parity. It is having impact on row parity and column parity. That's the reason it is possible to detect 1 bit error, because it is going to have syndrome as non-zero at the receiver side. So in 2-dimensional parity check, data is organized like this, and assume that this bit is changed. Previously it is 0, now it is changed to 1, and if you do this change, it is going to have an impact on row parity as well as the column parity. So then it is easily detected at the end by calculating the syndrome value. And similarly, if 2 bits are affected, whether this is going to identified at the receiver or not. So now if 2 bits, let us say 2 bits of one row is affected, so these 2 bits are corrupted. When these 2 bits are corrupted, that row parity is not changed, because when 2 bits are corrupted, it is neutralized. That we know already. When 2 ones are added or when 2 ones are removed from the unit, it is not going to change its parity, because even number of ones are subtracted. So that is the reason it is not caught in the row. But this is what the failure of first method, simple parity check, and but it need not to be same in column wise parity. So now we have changed 1 bit of this column, definitely it is impacting the column parity, and this column is going to have one more impact. So definitely it is going to have some impact, so that it is possible to detect 2 bit errors also. Two errors can be caught by identifying the changes in the column parity, and 1 bit error can be identified by identifying the changes in the column parity as well as row parity. So this way parities are get affected when content of the table is changed. Okay, so up to 2 bit errors it is working well. Now let us see whether 3 bit error can be caught or not. So if it is identified at any level, either row level or column level, if it is identified, then it is easy to detect the data received is wrong. Okay, let us see the third one. Now this diagram you see. Now 3 bits are changed during the data transmission. This entire table is sent to the receiver. Now receiver changes at the receiver, he got 3 changes. One is in first row, and in second and third also there are 2. So now if you observe very clearly, in second row and third row, the changes are corresponding to the same column. So it can be neutralized in column parity. So there is no change in the column parity when 2 bits of 2 rows are changed in the same position. When 2 bits of 2 rows are changed in the same position, it is not having any impact on column parity. Though it is not having impact on column parity, but it is immediately impacting the row parity, because only one change in the row, here also only one change in the row, and here there is one more change, and it is having impact on row parity as well as column parity. But this cannot be caught by the column parity, but it can be caught by the row parity. So this way 3 bit errors also easily detected with the help of this 2-dimensional parity check method. But comes to the point where we are failed in 2-bit parity check method means when you have 4 errors and 4 errors are corresponding to um, identical lines. Identical lines in the sense, if you take this methodology, there are 4 errors. So now these two, so it is not caught by the first row parity because 2 changes. Even number of changes never having impact on the parity. And here also 2 bits are changed and that is also not having impact on the row parity. But if you observe column, unfortunately those 2 corrections, whatever 2 corrections made to first row and the corrections made to third row, both are done in the same position. So this time what happens means 2 changes in one column, so it doesn't have any impact. 2 changes in one more column, doesn't have any impact. So that this type of errors cannot be detected because it is not impacting row wise parity or column wise parity. So this way up to 3-bit errors can be easily caught in 2-dimensional parity check method. So it is better as compared to previous method of simple parity check where it is only detecting odd bit errors, only detecting odd bit errors. It failed to detect even bit errors. So this way that method can be enhanced to identify more than 1 bit up to 3 bits, 1 bit error, 2 bit error, 3 bit errors. This can be caught easily in this method, 2-bit parity check. So this way we can conclude this one, 2-dimensional parity check method. And next we talk about one more method called Hamming code. Okay. And so far we are talking about error detection methods. Simple parity check is one of the block coding, linear block coding, and 2-dimensional parity check also linear block coding. For what? Detecting the errors, either it is detecting 1-bit error or 2-bit error or 3-bit error, but only it is applying the logic of detecting the error. But now we are coming to a topic where it is possible to correct the error also, So Hamming code is, main intention of Hamming code is it is intended to identify the error as well as correct the error, in which position that error is appeared. So these two things can be easily calculated in Hamming code. So as you already know the Hamming code, Hamming distance concept, Hamming distance is defined as the difference between 2 words or 2 code words, 2 bytes or 2 data and whatever it may be. So the difference means in how many positions those are differ. So if you perform XOR on 2 bits, 2 bytes, then you will get a number, and if you count once in that result, that becomes the Hamming distance. Okay. So now we need to identify one thing. If you have a minimum Hamming distance of 3, how it is related to that code size. Code size means n. So now if you have a minimum Hamming distance in a coding technique of 3, then it is going to detect 2-bit errors that we know from the formula called dmin is equal to s plus 1. Dmin is equal to s plus 1, where s number of errors can be detected. So if d minimum is 3, it is possible to detect up to 2-bit errors, but it is only possible to correct only 1-bit error. So Hamming code is going to correct only 1-bit error, and by having some enhancements, it is also identifying more than 1-bit error that we will see. Enhanced version of Hamming code will identify and correct more than 1 error. That's it. But Hamming code, in general Hamming code method, will identify the error and correct the error. That is only 1-bit errors are corrected. So now if d minimum is 3, now we try to make a relation between minimum Hamming distance and number of redundant bits added, So now if you take a data word of size n bits, in which k are data bits and r are the redundant bits or check bits, we call it as check bits. So now if you have a d minimum, that is Hamming distance, minimum Hamming distance, now that code word size is equivalent to 2 power m minus 1. If you have a d minimum of 3, then that code word n indicates code word, right? So code word size is n equal to 2 power m minus 1. So you are going to get a 7 bits here. If you want to maintain a minimum Hamming distance as 3, that code word will have 7. So 7 bits. So in these 7 bits, how many of them are for data and how many of them are for redundant bits means, so k equal to n minus 1 means k is nothing but bits for data, bits for data. So k is equal to n minus 1 where m is redundant bits. How many redundant bits means m. That's the reason we assumed where if m equal to r, if m equal to r, then the relation between data word size and minimum Hamming distance is like this. N is equivalent to 2 power m minus 1. And you can calculate data word size based on k equal to n minus 1. These are the equations which relates minimum Hamming distance with the size of the code word, and then you can calculate size of the data word with the help of k equal to n minus 1. So these relations must be maintained when you go for Hamming code. So let us see next slide where we will find a relation between redundant bits and this one. Okay. So this is one more slide which is explaining the same concept. It can be applied for any length, like there is no restriction on the length of the data units you take. It can correct and detect the single bit errors, that is one more thing. And the basic idea behind this Hamming code is Hamming distance. And as you know already, Hamming distance is calculated by performing XOR on two words or 2 bytes whatever you take, and the result 0 1 1, and the number of ones is nothing but Hamming distance. So likewise, so now if you observe this one, it is going to give a relation between how many number of redundant bits we need. The basic question is, I have a data unit. How many number of redundant bits I have to add? That purely depends on this equation. Okay, that total number of redundant bits must satisfy an equation, that is 2 power r must be greater than or equal to m plus r plus 1, where r is redundant bits, where m is message bits. Like if you have a data unit, how many bits are there in data unit? So if you know size of the data unit, and by substituting r values on which value this equation is get satisfied, those many number of redundant bits are required in order to maintain this Hamming code logic. So this way you can relate number of redundant bits versus bits of the message. This m indicates, don't confuse, m indicates message size. M bits are there in a data word. M bits are, previously we call it as k. So now we are calling it as m, that's it. So m is nothing but size of the data bits. When size of the data bits is given, redundant bits are calculated by using this equation. Okay. So let us see a table where it is going to show all the values. Let us see now number of data bits. I got only one bit data units. If you got only 1 bit data units, then this value is substituted in the equation, that is 2 power r greater than or equal to m plus r plus 1. This k value, the k value is substituted in that equation. So then what you are going to get is, you are going to get number of redundant bits required is 2. If you want to represent a data unit of size 1 bit, then we require 2 redundant bits. As per the Hamming code logic concern. That logic is shown in the previous slide. That logic is 2 power r. Yeah. Okay. So this equation you can observe. In this equation here, 2 power r greater than or equal to m plus r plus 1. Now what they are trying to give is, they are trying to give this m value. When m value is given, if it is 1, let us say if it is 1, then what is the r value? If you substitute r value as 1, here right hand side becomes 3, 1 plus 1 plus 1, 3, and 2 power 1, 2. 2 greater than or equal to 3, it's a wrong. Then on which r value this is going to satisfy the equation means, if m value is 1, now r value is, let us say r value is 2. 2 power 2 means 4. So m value is 1, r value is 2, and 1 is already there. So it is 4. 4 greater than or equal to 4. So when you have a data word of size 1, you require two redundant bits in Hamming code. So I will show you the table once again. Wait. So now when you have k as 2, k as 2 means number of bits in the data unit. If it is 2, again you substitute the 2 in previous equation, like 2 power r greater than or equal to this value k plus r plus 1. Previously it is m, so now I am calling it as k. Don't confuse. K or m both are representing this size of the message, okay. And in this case also, when you have k, the number of redundant bits are 3, so total code word size is k plus r 5. Now if you observe, if you got 3 bits, then also 3 bits of redundancy is enough. So this 3 is maintained up to 4. When you have a data word of size 4, then also we require 3 redundant bits only. Now whenever you come across data unit of size 5, then r must be 4. So in order to make that equation clear, so there we have written 2 power 4, it is 16. So 16 greater than or equal to which value? Let us say 7 bits. So 7 plus 4 plus 1. So it is giving 16 greater than or equal to 12. 16 greater than or equal to 12, it is true. So if you have a data unit of size 7, then you are going to get a redundant bits as 4, and totally code word is going to have a size of 7 plus 4, 11. So this way, when data word size is given to you, it is possible to calculate the number of redundant bits. That's the basic question. When we start our discussion of this Hamming coding, how many redundant bits we can add? Is it 1 or 2 or 3? That purely addressed with the help of this formula. 2 power r greater than or equal to number of bits for data unit plus r plus 1. Wherever that r is going to satisfy this equation, then those many number of redundant bits we require. So this table will show you up to data unit of size 7. So this way we can calculate the redundant bits for given data unit. Now comes to this one, the process of encoding and decoding at both sides. The process of encoder and decoder at sender and receiver. So if you take this one at sender side, what it is going to do is, so in this example, especially in this example, how many bits are there in data? 4 bits are there. When 4 bits are there in data, how many redundant bits are possible? From the previous table you can say 3 are possible. So you remember, when data word is having a size of 4, 2 power r greater than or equal to 4 plus r plus 1. Wherever that r is going to match that equation, then that r is considered as number of redundant bits. So in this case it is 3. So let me show again, go back to the table, see there. Data unit size is 4. When data unit size is 4, the number of redundant bits are 3. And finally that code word is going to have a size of 7. So this way, generator is having a functionality of calculating these redundant bits by considering we will see how what are the values of R0, R1, R2. We will see how this R0, R1, R2 are calculated. As of now, we need to give a conclusion how many redundant bits we need to add. That depends on the previous formula. And now the generator is going to have some equations in Hamming coding, and that equations will create values in this R0 field, R1 and R2 redundant bits. Okay. Now again same, whenever it is transmitted to the receiver, all these things are considered, like data word content and redundant bits content is taken, and all are given to the checker. And now this time checker will create a syndrome. And previously in simple parity check method, the syndrome is only 1 bit syndrome. If it is 0, no error. If it is 1, error. That is enough for detecting. But in this case, in Hamming code, it is not only for detecting, it is for error correction also. Error correction. That's the reason it has to give the position where that error is. In order to identify that position, syndrome is going to have 3 bits. When syndrome is having 3 bits, then it is going to represent up to 7, right? 2 power 3. 8 combinations, the maximum value is 7. So now, if you see in data unit, we got 7 positions. In data code word, we got 7 positions. These 7 positions are addressed with this syndrome. If syndrome is 0 in all positions like S0, S1, S2, all are 0, then no error is occurred in the transmission. And now, for example, if you got a non-zero at syndrome place like 011 or 110 or 101, that value will indicate the position of the error. And what we do is we go to that position and flip the value. Let us say it has given 101. 101 means what? 5. So fifth position, go to fifth position and correct it. Correct it in the sense we received 0. Correct one is what? 1. We flip the value and we take the value. This way, this error correction logic will work. So error correction logic is having a checker program. It takes the code word as an input and it creates a syndrome which is 3-bit syndrome, not 1-bit. 3-bit syndrome will indicate if 3-bit syndrome, all syndromes are having 0, no errors are received. If syndrome is non-zero, that non-zero will indicate the position of the error. And what we do is we go to that position and we flip the value so that we will get the correct correct data word back. So this way it works. So let us take some examples where you can understand more. Now the question is how these redundant bits are calculated. How these redundant bits are calculated. Now redundant bits are calculated at the sender side with the help of these equations, like R0 is calculated by doing this XOR on modulo 2 XOR on A0, A1, A2, and R1 is calculated based on these 3 equation R2. So likewise a predefined equations are there, and these equations are known to both parties, So whatever the equation we apply at sender side, the same equation is applied at the receiver side in order to calculate the syndrome value back. So see, if you observe there, R0 is a combination of A2, A1, A0, and S0 syndrome value is a combination of B2, B1, B0 along with the syndrome value, whatever the redundant bit sent, that is Q0 here. So this way it is going to have S0 is going to have one equation, and S1 is going to have another equation, and S2 is going to have one more equation. These equations are used at the receiver side in order to calculate the syndrome, So if you observe this equation, this last one is Q2, not Q0, it is Q2, because S0 is identified with this followed by Q0, and S1 is identified with the same equation followed by Q1, what we have received, and S2 is B1, B0, B3, and Q2 it is Q2. This way some set of equations are given, and these equations are used by sender and receiver to generate the values of redundant bits and syndrome bits. Now we want to give a clarity why only these equations means. You can have one more combination also, but these equations should maintain a principle of when 2 equations are added, it never leads to third one. That is a property of these equations. And every unit you take, every equation you take, it consisting of 3 bits of 4. 3 bits taken from 4-bit combination. So you got a data word of size 4, let us say, and if you have those A0 to A3, a equation should have at least 3 by leaving one out. This way you can prepare the equation. Once you prepare the equation, now when you do XOR on these two, let us say when I do XOR on R0 and R1, what I generate is A2 get cancel, A1 get cancel, I will get an equation of A3 plus A0. There is no equation A3 plus A0 in this set. So third one is not A3 plus A0, A3 plus A0 plus A1 also. So this way every equation is formed in such a way that it should involve 3 of the 4 bits in the data word, that is one, and it will create independent equations. Meaning of that independent equation means combination of 2 cannot create the third one. Combination of 2. So when you take R1 and R2, when you do XOR on it, which 2 are get cancelled? A1 is here in R2, A1 here, cancel. A3 and A3 both are cancelled. What is remained is A2 plus A0. There is no equation A2 plus A0 in the our redundant bit equation. So this way the equations are taken in such a way that every equation should involve 3 of 4 data bits. 3 of 4 data bits, that is one. And second one is no two equations when two equations are taken cannot create, by combining those two or by doing XOR on two equations, we cannot create the third one. That is the principle applied at a receiver side. And similarly at sender, it is at sender side. At receiver side, very simple. Whatever the bits you have given, all are added. And if all positions S0, S1, S2 gives 0, then no changes are there in the middle. And if it is giving a number like 011 or 110 or 101 non-zero, then there is an error, and that error position is indicated. There is an error, that error position is indicated with this syndrome value. So that is the logic of Hamming code. We'll see one example. So now when you apply the same equations what we have given in the previous slide, and when you apply those equations, you will get data word. Now what is the size of data word? 4. When you have a data word of 4, then what is, how many number of redundant bits are created? That should follow the equation like 2 power r greater than or equal to 4. 4 data bits plus r plus 1. It is satisfying. R value is 3. So that's the reason you got 3 code words. And how these 3 code words are calculated means based on the equations what we have given previously. This way the entire data words are added with redundant bits. 3 redundant bits are added to data words to make up a code word. Now let us see syndrome. Once syndrome is calculated, the syndrome value is taken by the logic logic of the decoder to determine where is the error. So these are the combinations. So if syndrome value is 0, no error, that I already told you. Now we need to identify one thing. When syndrome value is 001, it is Q0. Q0 is the bit which we want to update. When syndrome value is 010, Q1, and syndrome value is 011, then B2 is the one which is corrupted. So how we are going to determine? To this syndrome, this bit only corrected. This we need to understand. So if you observe this one, when the data is sent by merging redundant bits along with the data units, the redundant bits are merged at the positions of 2 power 0, 2 power 1, 2 power 2 likewise. 2 power 0 means the first redundant bit position number. 2 power 1, that is 2. In second position, that second redundant bit, that is redundant bit is set. Third redundant bit is set at 2 power 3. Okay. Redundant bits are not simply added at the end. So let us go to next slide and I will come back. Okay. I will show you this. Yeah. So if you observe this diagram, so here we got a data code word of size 11. So it indicates what we require 4 redundant bits. We require 4. This is another example. For the sake of understanding, I am showing this. So here, when this data is transferred to the receiver, redundant bits are placed in even number positions like 2 power 0 position, 2 power 1, 2 power 2, 2 power 3, likewise. These are the positions where redundant bits are placed. Now, the remaining data units are there now, like A0, A1, A2, A3, all data units are placed from this place. A0 is placed, A1, A2, A3, and leave that 8th bit A4, A5, A6, A7 likewise. So the preparation of code word is done in such a way that 2 power positions, 2 power 0 or 2 power 1 or 2 power 2, these positions are occupied by the redundant bits. Remaining positions are occupied by the data bits. Now let us go back to the example what we are talking about, this one. So now when there is an error, let us say at syndrome value is given with 1. When syndrome value is 1, it indicates that the problem is in Q0. The problem is in Q0. So why it is Q0? Why it is Q0 means, go back to the equations. That syndrome equations. On 001, why it is Q0? That's we want to understood. So 0 means S0 is 0, S1 is 0, and it is 1. Which value is having an impact of making this S0 0, S1 0, and Actually the order is like this: S0, S1, S2. So 0, 0, 1. 0, 0, 1 is given to 0, 0, 1 syndrome value is given to which we have to check. 0, 0, 1 is given to Q naught. 0, 0, 1 is given to Q naught. Why we will see by observing the equations. 0, 0, 1 means S2 is 0, S1 is 0 and S0 is 1. Now which field is having an impact of making S0 0, S0 1 and remaining 2 0, like if you observe these values, here we have Q naught, and wait, okay. So if you observe this equation S0, S1, S2, which field of this right hand side expression is capable of making this S0 0, S0 1 and remaining 2 to 0. So if you observe this equation, here you got Q naught. So Q naught only the one which is having impact on this S0 bit, and its impact is not there on S1 and S2. That's impact is not there on S1 and S2. So that what you can understand means when S0 is 1, and remaining 2 are zeros, these all are zeros, means these bit values are zeros. When these bit values are zeros, B1, B2, B3 are here existed, so that it is not having any impact. So B1, B2, B0 are zeros. So now in order to make this S0 1, Q naught must be 1, so that the change is made to Q naught. That's the reason at 0, 0, 1 position from this side, S2 is 0, 0, 1 position, the expected bit to be corrupted is Q naught, because 0, 0, 1 value is raised only because of Q naught. If Q naught is corrupted, let us say if Q naught is 1 and remaining all are zeros, then this S0 bit is set to 1. This way you can understand why that zero syndrome values are corresponding to different positions. Let me take one more also for the sake of understanding. Let us say 111. When syndrome value is 111, which bit is corrupted we need to identify. B1 is corrupted. Why B1 means if all are ones, which because of which bit this all becomes ones, means what is common for all, which is common for all of the equations, like S0 you take, B1 is there, S1 you take, B1 is there, S2 you take, B1 is there. So in order to make changes to all S0, S1, S2, one common variable is there, that is B1. That's the reason if you got 111 at S0, S1, S2 places, the bit corrupted becomes what? B1. The bit corrupted becomes B1. This way the syndrome table is prepared. So this is one, if you want to understand one more time. So let us take any of the bit. Let us say this 0, 0, 1, 0, 1, 1. How 0, 1, 1 is giving B2? 0, 1, 1 means this 0 indicates S2 bit, S1 and S0. The order is S2, next S1 and S0, from left to right. Okay. So now we will see how 0, 1, 1 leads to B2. So now we got 0, 1, 1. So 0, 1, 1. Now this equation becomes 0, means these two become 1 and 1, S0 1 and S1, because of which common variable this S0 and S1 are becoming 1, which is not present in S2. I repeat, when you have value 0, 1, 1, means that variable is making S0 and S1 to 1 and S2 to 0. Means it is appeared in S0, S1 but not in S2. It is appeared in S0 and S1 but not in S2. Which is appeared in S0 and S1, which is not there in S2, that is B2. So this way you can come across that table, values, syndrome values. So this way we can calculate the syndrome values, and in next video we talk about some of the examples how this is going to detect the errors, and how it is going to correct the errors. All these things we will see in next class. Let us stop up to this point.